Okay, thanks for the opportunity to speak here. I'm going to talk about joint work with Jeremy Miller that he already announced. So before I get started, I want to do a bit of philosophy. So the first bit of philosophy is, I wrote down a saying, which is hard work pays off later, but laziness pays off now, which is the first part of this talk. So we just want to quote the Cohen, May, Milgram, or Vasilyev for some homological stability result on C or Rn and get a result for all manifolds out of that. That's the first part of this talk. The philosophy of the second part of the talk about the Encells is, so I'm translating a saying from Dutch now, which is my native language, which is don't look a given cow into the mouth. By which I mean there's lots of structure around in all these types of examples, and you don't want to forget about that structure. Maybe you want to exploit that structure to get some more information about the object you're dealing with. So in particular, I will be looking at particular types of cell decompositions that use algebraic structure that Jeremy talked about. These EN algebras have some kind of algebraic structure, and I want to keep it into account in my cell decompositions. But mostly I want to talk about applications. So these will be about these bounded symmetric powers of C that Benson also talked about. So we're going to get some super cheap homological stability results there from our techniques here. Okay, so I'm going to do a very quick review of what Jeremy told you about factorization homology. Just a very quick one. So Jeremy gave you a construction that took as input some kind of n manifold and some En algebra, and as output it produced a space called the factorization homology of A over M. So the way you think of this is these are points in M with labels in A, and these points can collide with each other, and when they collide we keep track of the directions with which they collide, and the N algebra structure tells us how to get a new element of A out of that. That's the basic idea behind this construction. Okay, so Jeremy gave you one example, which I just want to state now to make things a bit clearer. So one example he gave was A being the natural numbers including 0, which is a commutative monoid under addition. Another way that I'd like to think of this guy is it's the same as the disjoint union over all k of the symmetric powers with k points in a disk. So symmetric powers of k points in a disk means there are k points in a disk, but they can be on top of each other. So these guys are clearly contractible because you can move all the points down to the origin. So that gives you this homotop equivalence. But this maybe explains the result of applying factorization homology to this En algebra, which is that if you do this construction, you get out the disjoint union of the symmetric powers. Right, so this is a way to take local constructions and make them into global constructions over manifolds. Okay, so one reason I talked about this example is that you may have noticed something here. This A naturally comes decomposed into different parts given by the number of particles, and the same thing happens for M, for applying factorization homology, if M is a connected manifold. So these symmetric powers are all connected if M is a connected manifold. So if this guy has a decomposition into different numbers of particles, or as we call it, different charges, the same will be true for the factorization homology over a connected manifold. Because, I mean, eventually I'm going to talk about homological stability. So I have to say, like, which components am I comparing? So that's why I'm now talking about charges here, to be able to talk about the different components I'm going to be comparing when I do homological stability. Okay, so the most important property of factorization homology, I think, is that it's locally determined, which means that if you have a manifold that is built by gluing together two manifolds, you can compute the value of factorization homology on that bigger manifold by taking factorization homology over the pieces and doing some construction to it, some bar construction. So I won't tell you the exact details of this theorem, but it does explain certain results. So the first result that it intuitively explains are these scanning results that Jeremy talked about. Right, so Jeremy proved that if you have some manifold M and it's open and connected, so open is needed to have these points brought in from infinity, these stabilization maps. So he proved that if you take the co-limit of a k, the homology of the k piece, the k charge piece, factorization homology, I should say. So as a convention, all my EN algebras are going to have connected components indexed by charge, just so I can talk about different components. So this means the part of the factorization homology that has charge A. So he proved that in the limit, as k goes to infinity, this thing is isomorphic to the homology of a component of some compactly supported mapping space. Okay, and the fact that factorization homology is locally determined intuitively explains this, because the group completion theorem says that this is true on Rn. So if it's true locally and this guy is locally determined, then you should expect it to be true on any manifold. Right? And the restriction open here comes from, well, it should at least be a manifold where the maps that are used in the local statement make sense. So that's where the openness comes from. So this is some kind of global version of group completion. Right, and this explains, I think you already mentioned, it explains McDuff's result about what the stable homology of unordered configuration spaces is. Okay, but that's a different type of result that I'll explain in terms of factorization homology. So one example of a theorem that I like a lot is Siegel's homological stability theorem for configuration spaces. So he proved that if M is open and connected, then if you take the homology of U conv k of M, there is a map which brings in one particle from infinity to the homology of U conv k plus 1 of M. He proved that this is an iso for star less than or equal to k over 2. Okay, so this is an ahistorical way of explaining this, but Jeremy showed, told you that these unordered configuration spaces also can be interpreted as some kind of factorization homology of the unordered configuration spaces of Rn. So as an ahistorical explanation of Siegel's theorem, you could say maybe Cohen proved that unordered configuration spaces of Rn have homological stability. So if factorization homology is locally determined, then maybe the same thing should be true of any manifold, at least where the maps make sense that you use in the statement of homological stability. Okay, so the theorem I want to talk about today, one of the theorems I want to talk about today, says that that's actually true. So the question that you might get based off Siegel's theorem is something like, is it true that if you take the components of factorization homology, that these have does this have homological stability if the components of A? So the answer is yes. So if you're in dimension at least 2, and the components of A are given by natural numbers, then the fact that the N algebra has homological stability is equivalent to the fact that the factorization homology of A has stability over all open connected manifolds. So I'll give quite a few examples of this in section 3. But I want to give one super easy example now. That gives you a result of Steenrod. Okay. So the example is, take A just to be the natural numbers again. Now, clearly this guy has homological stability because all the components are contractible. So all the stabilization maps are just going to be maps between contractible spaces, so in particular induce an isomorphism on homology each time. So our result then says that it clearly has stability. So our result now says that if you take this guy, take its factorization homology over an open connected manifold, that this has stability. Now, I mentioned before that these are just the disjoint unions of the symmetric powers of M. So this had now homological stability. You can even do slightly better. Because symmetric powers are homotopy invariant, you can take any CW complex, embed it in Rn, and take a regular neighborhood of it, which will be a manifold because it's an open subset of Rn. So you even get some results for, I guess, any Euclidean neighborhood retract out of this result, which is the theorem of Steenrod. So this was the theorem of Steenrod. Okay, so that was pretty easy. All right, that's a pretty. I find this a very beautiful application. So with very little work, you can actually get stability for some pretty interesting spaces out of this. So one comment I have is that we only work somehow in like a manifoldy topological setting. There should probably be theorems like this in a more algebraic setting, which give you more information involving weights and things like that. We don't know how to do that, but I think that would be very interesting if someone could figure that out. So how do you prove something like this, a result like this theorem here? So the idea that we have is that we want to take this factorization homology of A over M and try and resolve in the A direction, build A out of simpler pieces. Okay? And the idea is that we're going to approximate A by something that's built out of certain cells. The cells have to somehow involve the structure of an EN algebra, otherwise this makes no sense, and then use that filtration in terms of cells to prove this result inductively. So that's why I'm going to talk about EN cells. But I want to stress that EN cells aren't just a technical tool for proving a result like this. I think they're independently interesting because they seem to give more information outside of stable. You could characterize things about the homology of these EN algebras outside of the stable range in terms of where these EN cells are located. So maybe at the end I'll state a conjecture about that for mapping class groups. Okay. But now I want to talk about these special cells. So the basic thing we want to do is prove a theorem analogous to a theorem you know well about spaces, which is each space is weakly equivalent to a CW complex. We want to prove something similar in the world of EN algebras. So we have to figure out how to attach cells to an EN algebra we already have, so we can inductively build cell decompositions. So let me try and explain to you how you do one of these cell attachments. Okay. Okay, so we aren't like the most fancy people. So the first thing that we try to do is you just take A, you take your cell. So to attach a cell, you need some kind of attaching map. So maybe you just think, well, I'm going to take some map from the sphere into A. So one thing you could do is just on the level of spaces, attach a cell. Right? Maybe that's a good first guess. But this is no longer any N algebra. In particular, if I get some points that are in the interior of D, I don't know how to combine these things, the labels in the interior of D, if two points collide with each other. I haven't given you any prescription of how to do that. So in this case, we've lost the N algebra structure, and we somehow have to fix that. So pretty much we're going to do the cheapest possible thing. We're just going to freely adjoin all the operations that aren't defined. So let me say what that concretely means. Because I could state it in terms of some kind of scary infinity push out something, but that's not going to help anyone. I mean, that's not going to help us because we want to prove things about it. So we want a more concrete model. Okay, so what's the more concrete model? So what I do is I take particles in a disk with labels in this guy. This is just some space. And I'm going to say that these guys can only collide with each other if the composition is well defined. So just as a sanity check, say I attach nothing at all to A, and I make this definition. So I get some particles in a disk labeled by A, and they can only collide if collision makes sense, which is always. Do I get the same thing back? Well, that would be an ideal thing. Well, it's not going to be homeomorphic to it, but maybe in topology you don't care so much about that. But it is going to be homotopy equivalent, because what you can do is you can move all of the labels to the origin in the disk and just let them collide with each other there, and you get back a homotopy. Okay. So maybe just a picture. You have some points. Some of them are labeled by elements of A. Some are labeled by elements of the disk. And say we don't change the labels at all, then these guys are allowed to collide with each other, but these things can't collide with anything. But what could happen is that we also move in a space of labels into A, and then at that point these guys can collide. Okay. So that thing is something we call an Encell attachment. And at some point I come up with a notation. This notation, because I think it's a next symbol in like the LaTeX editor after the cup. Okay. So, any questions about this definition? Maybe just to make clear, this guy actually is in the N algebra, because if you get a picture like this, a couple of pictures like this, an element of the little n-disk operator Jeremy talked about, which are just some circles, or just some disks in a bigger disk. I can just take all these pictures and put them in that place and get a new element. So this will be in the N algebra now. Okay. So just like every space has a cell decomposition, up to weak equivalence. Every En algebra has an En cell decomposition. So if you have a space and you know something about its cell decomposition, that gives you a lot of information about a space. Say you only know you have cells above a certain dimension, then you know that there's no homology below below that dimension. And so what we're going to do is we're going to characterize homological stability in terms of where these cells are attached. That's going to be the second theorem. I should have said here.
How difficult is this? This seems surprising.
This is not so difficult. Also, I didn't really completely finish the statement here, which I just noticed when I looked at my notes. So I just told you just how to attach an Encell, but I didn't tell you where you got started. So in the case of space, you start with some point, or maybe if your space is not connected with a multiple set of more than one point, and you attach stuff to that. So here you also have to get started somewhere. And the place where we're going to get started is, maybe now you can see where homological stability comes in, by that Encell decomposition, by attaching cells to the unordered configuration spaces. So this is a statement, I guess, when pi 0 of the En algebra is given by natural numbers. Otherwise, you need multiple color configuration spaces. So you conf of disk.
Yeah, there's the idea here that like the configuration spaces are like the free En algebra.
Yeah.
And sort of, so those are your generators. Like in the billion group, you take the free of the billion group on that, and then you're putting in these cells, or those are your relations.
Yeah. You just inductively build this guy and make it more and more connected. The map between them. Okay. So the second theorem I'm going to state says that homological stability is equivalent to having a certain type of cell decomposition in this sense. And I think that's not just like a technical tool, but actually an interesting characterization of homological stability for these types of guys. Okay. Again, we have to be in dimension at least 2. And here's some slight irritation, so that we have to work in chain complexes. And that has to do with the fact that you could conceive of some irritating En algebras that have like pi 1 changing around a lot, and something that you might not necessarily be able to see on the level of homology. And we don't want that type of stuff to get in our way. So we work in chain complexes instead of top, but you can pretty much ignore that. The reason that it's not a bad thing is that if you care about homological stability, you never really cared about the space itself anyway. You only cared about its chains. So the theorem is that A has stability if and only if, I guess you should say pi 0 of A is in 0. Only if A has an Encell decomposition such that all the Encells of dimension D, so I guess here this guy was dimension n, if all these guys are attached in finitely many charges. So charge referred to these different components. If I have to specify an attaching map here, except if you're dealing with a zero sphere, which you have to, we're just going to impose that goes to a single component. All these attaching maps go to a particular component. We call that the charge of a cell. So what this is saying is that if you draw a graph and you put a dimension here and you put a charge here, then there's going to be some kind of line like that, or maybe that's a bit optimistic. Some kind of line like this, and all the cells are attached in this region. Okay. So, and then we prove that this gives you the stability factorization homology. So the idea, I already mentioned the idea of how to do this proof. I'm not going to do it in detail. I just want to get to examples and applications of this. But the idea is that the reason Jeremy was like doing this giant construction with all the bars and stuff is because the fatter you make things in topology, the more likely to be that the more likely it is that they're actually homotopy invariant. So you can replace this guy by its cell decomposition once you make like a sufficiently flabby model of factorization homology. And now the cell decomposition gives you a filtration on this construction, and you can inductively prove that each time you attach a cell, you keep having homological stability, starting with the base case of configuration spaces, where we have Siegel's result. Okay. Now I want to get to examples. So when I started writing this talk, and it's actually still on my notes here, I wrote down an apology for only doing things in dimension 2, saying that like dimension 2 is the easiest, and there's some nice geometric properties about dimension 2, like symmetric products are manifold, symmetric powers are manifolds, so everything becomes a lot easier. But it seems like here people think dimension 2 is probably the most interesting one anyway. So I think that apology is not really warranted. Okay. So applications. So the first one is laziness. You can use local computations to get global results. So one of the spaces that Benson talked about, and I use a slightly different notation, are these bounded symmetric powers, say of the complex plane. So this is the subset where there can be at most endpoints in the same place. Which is the same as the space of monic complex polynomials. Of degree, I guess I didn't say degree. The degree is the component you're in, with roots of multiplicity less than or equal to n. Or no roots of multiplicity greater than or equal to n minus 1, n plus 1. Okay. So, as we saw before, the homology of these spaces was computed by Cohen, May, and Milgram, and Vasilyev. It's too bad that I erased this. Okay, so CCMM and Vasilyev just computed the homology of these guys. And you can read of homological stability from that. Or you can maybe use Benson's result now rationally to get homological stability for this guy. So now the version of the first thing that I mentioned, if you have stability locally, you get it over any open connected manifold. Now it gives you the following result just essentially for free. If sigma is an open and connected surface, then if you take these bounded symmetric powers of your surface, these have stability. So one thing I didn't mention, you can, if you're more careful, you can go through all these theorems and get ranges. So homological stability range has to do with like the slope of the line above which all cells are attached. So you can also get explicit ranges out of this. You can even do some trickery to get the closed manifolds rationally using transfers, but maybe I shouldn't talk about that.
How easy is it in practice to produce an Encell decomposition?
I'm going to talk about one in a minute.
Okay.
It's really hard.
Right.
Except in dimension 2. Except in dimension 2.
Are there cases where you can disprove stability where it wasn't known by producing a particular cell decomposition? Because right now I can see we've got the result of stability and it says, okay, there must be a cell decomposition. You get this right of this type by the theorem, and then you can sort of go looking for one. But if you had an instance where you didn't know that was the case, could you please do it?
Yes, but it's a bit tricky. Maybe I'll say some words about it at the end.
All right.
So is it easier than actually just computing the dark homology groups?
Computing the full thing is really hard. Getting bounds it's not really finished yet, but we're working on showing that that's equivalent to some kind of complex being highly connected, the thing that you expect there to be true from homological stability anyway.
I'll usually say the theorem provisionally due to Yamaguchi, we get a better range.
Oh, what Jeremy said is true. Okay, so this is one cheap thing you get just from these techniques. So now a second application, which is how do you find an Encell decomposition? Which I can do in one particular case. And the story of this is that we figured out how to do it in one particular example. So it's again going to be for these bounded symmetric powers. So we found it for one example. And then Soren heard from Jacob how to do it or something. So eventually we heard the idea from Soren and were able to compute it. Okay. So the previous example that I had, where I showed that these guys have homological stability just by computation, also shows that these guys, these bounded symmetric powers, that they have one of these nice cell decompositions. But what is it actually? So we can compute it if, here's a slight technical detail that was completely ignored by Jeremy and me, is that this thing depends on what tangential structure you're dealing with on your manifold. And now we're working with oriented manifolds, so this is really the framed little n disk operand. So at this point we have to switch from the framed little n disk operand to the little n disk operand, which means working with framed manifolds because of a terrible choice in notation someone made in the 80s. But I'm just going to say some words, but you can just ignore these. So we can compute. You can compute one if we replace. If we replace the framed En by the little n disk operand Dn. So just, if you don't know what this means, just imagine that these are the same symbols. It's going to be fine. Okay, so the claim is that there exists a D2 cell decomposition of this guy with one D2 cell in each dimension 0, 2, 4 to 2n minus 1. And these guys are in charge in charge is 1 up to n. Wait, does this work out? I think it needs 0. Sorry, yeah. Okay. So let me give a sketch of the proof. But the only thing that I won't actually prove are some formal properties that are maybe of these cell attachments that might be not so hard to believe. Okay. So the case, do it by induction on n. So the case n is 1 is essentially the definition. Taking a 0 cell in charge 1 gives you the free D2 algebra on a point, which is the configuration space. If I used framed E2 here for the experts, I would have got some kind of labeled configuration space, which is not what I want. Okay, so this is true because if you take sim less than or equal to 1 of C, then that's the same as uconf C. Okay? So for the induction step, the first thing that you note is that if you take the symmetric powers bounded by n, then this guy can be obtained by the the D2 completion of the partial monoid. Okay, that sounds a bit scary. But it just means take a disk, take points in it labeled by these numbers, and only allow points to collide when that collision makes sense. Which gives you points in a disk labeled by these numbers that can collide, but they can't ever get above n, which is exactly what this symmetric guy is supposed to be. Okay? So this thing here, this statement here, implies that whatever D2 cells there are, they're going to be in charge less than or equal to n. So that's the thing you have to prove. The only reason why this is a sketch of a proof. Okay. So now what you notice that sim less than or equal to n of C is equivalent to sim less than or equal to n minus 1 of C in charge less than or equal to n minus 1. Because they're both contractible there. Right? If you have less than or equal to n minus 1 particles and you're allowed to collide them, you can just move all of them to the origin and let them collide there. So the only place where this guy is different from this guy, if you only look at these particular components, is in the last component. So we have to fix up that guy to become contractible. So this means that we need to figure out what we need to attach to the n plus 1 component, or the n component, to make it contractible. We need to figure out what to attach to the n component of sim less than or equal to n of C to make it contractible. Okay, but this guy is homotopy equivalent to S2n minus 3. So fortunately I erased the statement of the result, but it basically means that we had all these cells already in charge less than or equal to n minus 1. And we need to kill off this thing by attaching one more the n cell. Well, attaching the n cell is going to cause lots of random things to happen in higher charges. With the charge you attach it, it's just going to be a cell attachment. So just attaching a single cell here is going to give us the correct cell decomposition. So we need one more cell in charge n plus charge n and dimension 2n minus 2. Okay. So what we found here is the cell decomposition of these bounded symmetric powers that in particular has this property I talked about before, which is that for each given dimension there's only finitely many charges in which cells are attached. In this case we only attach one in each dimension, so at most. So that's definitely true. So you get homological stability out of this by the second theorem that I stated. Okay. So I have 4 minutes left. So what I'm going to do is state one example, but then maybe make a conjecture about mapping class groups.
Hold up this example is that so if you have an Encell decomposition, you get it actual cell decomposition, you have multi looping and shifting. And so like the multi looping of this guy is CBN, which has cells of even degrees. And we're saying this can be promoted as EN cells, EN algebra. And you get cells of even degrees. Now they're EN.
Yeah, maybe someone here read Rotation Invariance in Algebraic K-Theory by Jacob Lurie. He does something similar. That's why this cell decomposition comes from. Okay. So the third example I was going to talk about was a bit more tricky, but the idea is the following. So Benson talked about these spaces, pointed rational maps from, well, he did CP1 to CPn. I'm just going to do CP1 to CP1. And these are the degree k guys. So this is the same as space of two monic polynomials without a common root. So really this is some kind of configuration space where you have particles of two different colors, one coming from the roots of the first polynomial, the second coming from the roots of the second polynomial. These particles can collide with particles of the same color, because we don't care about the roots of these polynomials coinciding, but they can't collide with each other. So two different colors can't collide, because then the roots would coincide here. Okay? So one way of writing that is that it's the D2 completion of N0 wedge N0. This is a partial monoid, and you only know how to add things that are in the same N0. You don't know how to add things that are different colors. Okay? So now, just quickly, the trickery is going to be that these guys, these N0s have homological stability just because all the components are contractible. So they have a nice cell decomposition, which means that these guys wedged together have a nice cell decomposition, which means that the completion has a nice cell decomposition. Just all of this is just like formal trickery, which means that by our result, these spaces have homological stability. So you get Siegel's result essentially for free from the fact that the components of the natural numbers are contractible. Okay. So finally I wanted to state one conjecture, which is, it has to do with maybe some of the reasons behind pursuing all this stuff. So here, Jeremy talked about maybe the coolest example of an E2 algebra, which is take the classifying spaces of the mapping class group of a surface of genus G with one boundary component. You can make this into an E2 algebra by taking disks with disks in them and then gluing in these surfaces along their boundary to that disk. Okay? So here's the most optimistic conjecture, and it's like probably false, and I have no idea how to prove it. But heuristics say that this guy has an E2 cell decomposition with cells in dimension d at least 2g minus 5. Which maybe doesn't excite everyone as much as it does me, but this is like far out into like the unstable range. So something like this, it's unclear like what it exactly says about the homology of mapping class groups, but at least would give some kind of information about what happens in the unstable range. So maybe at some point we'll prove this, hopefully.
Didn't think or imply how much was space mapping class groups in there.
Yeah.
What?
You have to be careful because there's this minus 5 is irritating. So yes, but you have to feed in low dimensional computations. You have to like know the homology of the first 3 genus guys in like the first 3 degrees or something. Yeah, it's not that super hard, but you can get it from there. So this even might give you a better range than you originally expect, but that like those things give obstructions, and that's where you get the 2/3 from because of a particular class in homological degree 2 and genus 3. Okay. Any questions?
All right, now the question.
So would sort of metaphysically this sort of imply that these things were sort of determined by these first 3 genes? Like, is there like there'd be like a metastable range in which they were sort of controlled interaction things?
It's a bit hard to, I mean, on level of homology. The point is, one thing that makes this tricky is that these cells live on maybe a topological or a chain level. So when you pass to homology, there's going to be lots of complicated stuff they're going to contribute and cancel out, and like some things get cancelled out twice, so you get a new class in 1 degree higher based on that. So I don't know exactly what this is going to tell you about the homology, but maybe this is like the statement that actually is an interesting statement. I don't know. Maybe you can't do better than this. But yeah, somehow it does say that like in terms of homology, these low degrees are actually what's causing all of the non-stability in a large range at least.
Are there other things that like having Encell decomposition sort of gets for you? I mean, sort of suppose you're in a situation where like you have homological stability and then you have your theorems that sort of gives you the cell decomposition. Like, what kinds of things can you do with that?
So it should be the case. We don't know what the precise best statement is, but so the thing I just said something about like, oh, there's some line above which all your cells lie. If you know a particular slope of that line, you can get ranges out of this. But we also expect that if you know even more, like if the slope is particularly high, then you get results about metastable homology. Like the relative homology of the stabilization map is going to again stabilize in a range by degree shifting maps, that type of stuff. I expect you to be able to get something out of that.
Okay, let's thank our speaker again.